All right, so I'm going to talk about noise, mainly noise, and then transients and anomalies in radio astronomy. And most of my talk is going to be about radio astronomy, but I'll also briefly touch upon some aspects of machine learning in astronomy as well, including a couple of slides from my colleague. Right. So my research is on transients, and in particular, we study these things called fast radio bursts. So this is an animation of what fast radio bursts would look on the sky if your eyes were sensitive to radio. They're basically just flashes of light. They last somewhere between microseconds to milliseconds, and there are 1,000 of them every day in the entire sky. Okay, and surprisingly, we detected these only in the past 15 years or so. We did not know about their existence before that. And some of these can be incredibly bright. They can be as bright as cell phone signals, except that they're not coming from a tower 10 kilometers away. They're coming from halfway across the universe. Okay, and we have no idea what causes these. Some FRBs repeat, so there'll be flashes from the same location in the sky with some of the same characteristics. Some of them don't. There's a flash and it's gone, and we haven't seen it repeat pretty much ever, right? So within our observation, it hasn't repeated. So you might ask, why are these transients interesting? Well, for one, we don't know what they are, so we want to find out. There's a big bang. And the other thing is that they are, to be visible from cosmological distances, they have to be 1 trillion times brighter, more luminous than the pulsars which we know of. So there are these pulsars. This is sort of a neutron star which is rotating, and it has a lighthouse kind of effect. And every time the beam points towards us, we get a flash of light. We know about these for about 70 years. And we have some idea of how the emission works, right? But we know these only within our galactic neighborhood. We cannot detect pulsars farther than a few tens of kiloparsecs away. These things are coming from gigaparsecs away, right? And because they're traversing this entire universe, they are potential probes of matter, magnetic fields, and the structure in the universe. You can probe basically every electron and magnetic field that the radio wave passes through. And then they're also could be linked to other transients. We don't know what produces an FRB, but there are a lot of different models, most of them which involve neutron stars, but there are also quite a few things which involve exotic physics, axion nuggets and string cusps. I think Sandeep would know more about that than me, but there are a lot of different models. There are about 70 different models for FRBs, and we have no idea what these are. So today, my talk is not going to be about how we extract science from these observations using machine learning. The machine learning is actually what enables us to do this science in the presence of anthropogenic noise or radio frequency interference, which is RFI. So how do we search for FRBs? So one thing that we get is called dispersion, which means that light travels differently at different frequencies. In the case of radio waves passing through plasma, high frequency radio waves travel faster. So what we get typically from the telescope is a dynamic spectrum, which is shown on the top right here. And this grayscale is basically the intensity as a function of frequency on the vertical axis and time on the horizontal axis. And you can see that the pulse arrives earlier at high frequencies because the high frequencies have traveled faster, and it arrives later at low frequencies. Now the shape of this curve is very well understood from physics. It is frequency to the -2. But the magnitude of the shift depends on the number of electrons that the wave interacts with from the source to the observer. So it's just integrating the number of electrons, right? And if you know the dispersion measure, you can say you can figure out, you can integrate this intensity across frequency, and you can come up with something called the time profile, right? But if you don't know the dispersion a priori, so you have to search for it, and you have to find exactly which dispersion measure you get the pulse at, right? And this signal is extremely sparse. The dispersion can be 20 to 30 seconds. So the sweep actually comes across 20 to 30 seconds, but the signal width is only a millisecond, or can be even smaller, right? So you have a signal dilution of 10 to the 4 or more, right? Also, because of certain technical reasons, you have to have 16,000, you have to have a lot of frequency channels, right? So in the case of this telescope CHIME, which I work on, and I'm going to talk mostly about, you have about 16,000 frequency channels in this dynamic spectrum, which means that the signal to noise ratio is spread out across these 16,000 channels, and the SNR in each channel is about 0.1. So again, you're mostly looking at extremely diluted, sparse signals. So the way this CHIME telescope operates is that you're looking at a video camera on the sky, right? Instead of RGB, there's 3 colors. You have 16,000 different colors, right? And instead of taking images at 30 frames per second, you're taking 1,000 frames per second. And instead of having a megapixel camera, you have a much more modest thing. There are about 1,024 pixels, which each pixel is, we call a beam, right? And the data rate coming out is about 800 gigabytes per second. That's about 1 petabyte every 20 minutes. Clearly, you can't store this data, so we have to process all of this in real time. And all of that is done in these shipping containers where we have a few hundred computers sitting in there with GPUs and CPUs. And you do all of this and you barely detect 2 to 3 FRBs per day, right? So there are a huge number of FRBs yet to be detected. And this is the highest rate of FRB detection, which we have achieved with CHIME. Other telescopes in the world detect 1 FRB every few weeks or so, okay? Now, the way you do FRB detection is you have to do a lot of data cleaning because most of your data is just noise and crap, right? Then you do de-dispersion, and you have put a loop here because you have to do different dispersion trials. You try for different dispersion measures. Then you do a matched filtering where you say, okay, is there something which goes blip in my time profile? And you do that for each dispersion trial as a function of time. Then you do some clustering and classification. You say, I'm getting these signals from these different pathways. Are these interesting, right? And then you ask, is this astrophysical at all, or is this still from terrestrial sources? And then you can try to figure out what its physical properties, and you can try to do science with it. And machine learning can apply in multiple stages of this. In pretty much every stage, we can add machine learning. Some of it we have already implemented. I will highlight a couple of things which we haven't implemented, we have thought about, but we have not had the resources to do. Right. So machine learning is used to classify RFI or radio frequency interference versus astrophysical signals. And we have achieved, figuring out one part of astrophysical signal in a million RFI events, right, with a precision of 99% and a completeness of about 95%. That's a little bit SNR dependent. SNR is signal to noise ratio. We have also used CNNs to process the dynamic spectra directly. You take the dynamic spectrum, pass it through a CNN like this. In this case, you have a CNN, you have a you have a dynamic spectrum here, you have a dispersed spectrum here, and then you pass it through a CNN and you try to identify if something is interesting or not. But this is assuming a particular shape of FRBs. I'll come to that a bit more later. We are now slowly getting into using these sort of CNNs for classification and understanding the physical properties of FRBs. Yeah. Right. So now let's talk about what sort of things we can do. One thing is that FRBs come in very different shapes. This used to be the quintessential shape of an FRB. It's broadband, it's visible across all frequencies, it's very narrow, and you have this nice scattering tail. But turns out FRBs come in all sorts of shapes and forms, right? We have these narrow band ones. There are things with multiple components. This is something called a sad trombone, which seems to go down in frequency. You have these components which are always marching down in frequency. And we have some hand-wavy evidence that most of the times we see these kinds of bursts from non-repeaters, and most of the times we see these kinds of bursts from repeaters. So there can be some sort of a astrophysical source difference as well. So again, I'm putting up a gallery of these FRBs. You have these kinds of things which are very narrow band. You have these very exotic things with one in 3,000 FRBs is like this. So where you have these multiple components, right? And it's very periodic. So could these be coming from different sources? Could this be a merger of 2 neutron stars, right? Could there be similar multi-wavelength events which we need to look for? That's what we want to try to identify very quickly. And this has been done before for gamma ray bursts or GRBs. So gamma ray bursts come in 2 types. There are short gamma ray bursts and long gamma ray bursts. And the original classification was basically on the duration itself, right? So short gamma ray bursts occur in hundreds of milliseconds. Long gamma ray bursts occur from 2 to 1,000 seconds. And it turns out that if you do a TSNE clustering of these light curves at different energies, so you're plotting at different X-ray energies, you can plot the light curves, and you can do a TSNE clustering of this 4-dimensional space into a 2-dimensional space, and you get very clear distinctions between these 2 types of sources, right? And what is interesting is that the time scale, if you look at, actually has overlap. So you can have short GRBs which are actually long, and long GRBs which are actually short in time, right? So there can be similar things which can be done for FRBs, and this is something which I'm working on with my student Ajay Kumar and a colleague Ashish Mahabar. Right. The next part is the bane of our existence, which is radio frequency interference. There is anthropogenic signals from all sorts of things, TV stations, cell phones. But there's a timer now. I'm sorry about that. I didn't notice. Sorry. So there are satellites, aircraft, all sorts of things, right? Transformers, even bad connections between transformers. High voltage lines will cause sparking, which causes broadband RFI. And you see all sorts of weird signals. These are just a very small sample of examples. And this is particularly important for a telescope like GMRT, which sits in the Pune-Nashik region, which is developing rapidly. There is a lot of industrialization that is happening. And of course, we can't prevent industrialization. So we have to make sure that we can work with RFI, right? So the ratio of finding these transients is 1 in 10 to the 7 or so. So you really have to work hard to find transients in RFI. There's also a dynamic range problem. RFI is far brighter than the transients that you're trying to search for, right? So here are a couple of ideas. We are currently processing each beam on the sky independently, right? So you have intensity as a function of frequency and time, but between multiple beams, the distribution of RFI intensities and the distribution of astrophysical intensities can be different, right? Because if you have a camera which is focused on the sky, a star will be sharp, right? You will have it'll be, most of its light falls on 1 pixel. But if you have somebody puts a flashlight next to the camera, the glare will be across multiple pixels. So you have a defocused image versus a focused image, right? So it's kind of similar. You have RFI, which is local to you, which is within a few kilometers of your telescope. That's in the near field. Astrophysical sources are in the far field, right? So you can try to understand what the differences are in the distribution of these intensities. So you can imagine you take a bunch of different beams and you put it in through a neural network black box and ask what fraction of the intensity in this pixel is because of astrophysical signal and what fraction of it is because of local RFI, and can we subtract it correctly, right? And this is obviously has to be robust to different RFI shapes, different sources of RFI. There could be a car here, a transformer there, and so on. The other thing is you can do some sort of anomaly detection. Right now we are assuming that FRBs are these nice broadband shapes. We necessarily have clean dispersion. We have a time profile which looks the way we want it to. We are assuming just a slight blip. But what if there are periodic signals which are really broad? We don't know what. There is a danger that we'll find exactly what we were out to find. We made a pipeline to find FRBs of a certain type. We found them. But what about the missing ones? Right? So you could imagine you can do some sort of an anomaly detection. You can look at the same data and ask, is there some sort of transient, irrespective of the shape or intensity, which is not RFI, which is something that comes and goes very quickly, right? So you can just take this same data and push it through another system which would detect anomalies. Right. So now let me talk a little bit about the efforts that we have ongoing at GMRT, and Div is leading this working group. There is a lot of effort for mitigating RFI around GMRT. GMRT sits in a circle of 15-kilometer radius. There are 30 antennas distributed here. 13 of them are right in the center. And there are a lot of villages and towns in here. The Pune-Nashik railway and highway are going to pass through here. And there's a lot of activity going on. And this RFI doesn't just affect transient science, it affects all observations. So if you're doing spectral line observations of galaxies, if you're trying to understand galaxy mergers, all of this is going to affect the sensitivity and the efficiency of uGMRT. And this is, of course, going to get worse with the introduction of 5G and 6G and so on. So one of the things that we do is local outreach and education, make sure that the farmers are using the correct kind of LED bulbs and so on. But we also need to actually implement systems in the telescope which can get rid of RFI. So there is some part of that is already done with analog systems. We can build filters to take out the police wireless band and so on. The Kaushal Buch and others have made digital systems which can remove RFI at the FPGA level. But new RFI will keep propping up. So we have to identify new RFI as it comes along, find where it is, go there and tell them to stop it, right? So we have to identify, so the question is, can we identify new sources of RFI from antenna level data, right? Can we subtract this RFI from the data in real time? Can we use satellite imagery? We started a small thing where we are doing this manually right now, but can we look at images, satellite images, and see, okay, there's a new industrial development coming up at this location, so we better go and check out what they are doing. Right. So now let me change tack a little bit. These are slides from my colleague Yogesh Vadadekar, who is also online, if in case I butcher the explanations. But there is a lot of machine learning which is already done for doing science from catalogs and images. So you can imagine that you have different types of galaxies, and you have images of different types of galaxies. For example, the ones shown here, and you want to classify the morphologies of these galaxies because they refer to different science cases. So that has successfully been done with optical images, with radio images. You can also do regression. So one of the things that happens, this is what Shravan mentioned in his talk and Girish mentioned in his talk as well, is that we have a fairly good understanding of stellar and galaxy properties. And there are astrophysical models which will tell you, given the galaxy with this kind of a star formation history and so on, this is what the observation should look like. That's reasonably easy to do. But doing the reverse is very hard. That's very computationally intensive. So the part is, can you take observations, so catalogs and images, which can often be sparse. So maybe you observed this galaxy with this telescope, but I observed this galaxy with another telescope. Can I combine this sort of sparse and varied information together to go back to stellar and galaxy properties, right? And so these are a bunch of publications which you can refer to for Yogesh's work. And with that, I will stop here with this summary slide. There are 4 different aspects which I talked about. Mostly our work right now is in enabling science and keeping it working through increasing development in India, right? And still letting us do our job. So if anybody has any questions, come and talk to me. Thank you.